In video number 276, we learned how to use the Smith chart to design an L matching network to match a load impedance of 33 minus J51 ohms to the system impedance of 50 ohms. And for a network such as a shunt L and a series C, we wound up with component values of about 470 nanofarad and 200 picofarads for our particular operating frequency of 14.2 megahertz. Now you may recall we chose this network based on this set of yin-yang diagrams here that said if our load impedance was down in this area, we could use a shunt L series C or a series L and shunt C network, and we chose to do this one. If we examine our yin-yang diagrams here, we can see that for the load impedance that we were talking about, there's actually four different networks that we could use to match that impedance. We could use the one we chose, we could use this one over here, but also our load impedance fell into this area here, so we could use a shunt L series L or a series and shunt L. So rather than go through and use the Smith chart manually to show you each of those potential matching circuits, I'm going to introduce you to probably one of the best Smith chart simulator programs for the PC that I've come across, called SimSmith. Let's start off by replicating what we did on paper with the shunt L and series C network. SimSmith is a fantastic free Smith chart simulator that was written by Ed Harriman, AE6TY. Another great resource to look at is the YouTube channel of Larry Benko, W0QE. He has a whole series of tutorials on how to use SimSmith, and I'll include links to these down below. Now let's start off by just replicating the experiment we did on paper. So I've included my operating frequency of 14.2 megahertz here on the source, and here's our load impedance that we're starting off with, 33 ohms minus J51. And you notice that plot's right down here. And remember, we're going to start off by replicating what we did earlier. So that is starting off with a shunt L, so I'll just grab the shunt L and stick it up here. And you notice that traces this trajectory up along essentially the constant conductance circles. And if I mouse over the value for the inductor, I can roll its value back and forth. And the idea here is to roll it up, in this case, up to our constant resistance circle that passes through unity. And that's pretty darn close. So now I want to add my series C. So I grab the series C, drop that in series here between the generator and the load. And you can see that we're just about at the matching point here. I simply just roll the value of that capacitor up or down, and boom. Very simply, we've replicated that same 470 nanohenry and 200 picofarad L matching network that we did on paper. Well, now that was really simple to get to that same result that we did on paper. So let's use this program to show us what the components would be for the other three possibilities of the matching networks. So let's start off by designing this network now, which would be a series L and a shunt C. So we'll go in here, and I can just simply grab these guys and drop them down into the trash can here over here and start over. Now let's add a series L to begin with, and we see that's rotating us up here. Now since the next element we're going to add is a shunt element, we're going to go on these constant conductance circles, so I know I need to bring this point up to that constant conductance circle. So I'll just roll this inductance value until I reach the unity conductance circle right there. Okay, now I could add my shunt C in front of this network here. And we went a little bit too far there, so we'll just rotate our shunt capacitor value back, and boom, there we are, perfectly matched, and about 834 nanohenries and 157 picofarads. So real simple, we've been able to design two of the four matching networks. Let's do the other two. Now the other two are purely inductant networks, a shunt L and series L, or a series L and shunt L. So let's go design each of those. Alright, let's do the one with a series L shunt L first. So let's stick the series L in series with the load here. And again, I'm going to remember L's kind of bring us up on the Smith chart, so I want to rotate up to the unity conductance circle here. So we need to change this inductance value, until I reach that unity conductance circle right here. And now I'll add the shunt L component to the front of that and adjust its value till I get down to my match point. And there I am, impedance matched with an L network that's purely made of inductors, 300 nanohenries and 786 nanohenries. And lastly, let's do the network that starts off with a inductor in parallel with the load. And we're going to adjust that inductor value so that we hit the constant resistance circle down below the real axis here, so that when I add my series inductor, we can rotate up to our match point. And we can see, using this style of network here, we've got about 2.9 microhenries and 619 nanohenries. So we can see it was very easy to whip through the 4 possible combinations of our matching network for that particular load, and have got 4 different sets of values of components. Now, which one do you choose? Again, it may largely be determined by the component values you have available. In the case of this last matching network, I'm not real crazy about using a very large value inductor here because of the parasitics involved, so I probably wouldn't use that network. I might choose, for example, to use this network here because this is a high-pass network. Or I might choose to use this network here because this is a low-pass network, and that might help to reduce any harmonics that might be coming from my emitter or something like that. So at the end of the day, you have some flexibility in determining which of the matching networks you want to use for your particular situation. And using a really cool program like SimSmith makes it very easy to do this what-if type of analysis and develop a couple of different alternatives for your particular matching network. Again, I will put links to Larry Benko's excellent YouTube channel that has a lot of tutorials on this great program that was written by Ed Harriman, AE6TY. I also put a link to Ed's website as well, where you can download SimSmith for yourself. If you liked the video, give me a thumbs up. If you haven't subscribed already, please do so. And thanks again, as always, for watching.